Innovation in Instagram's recommendation system is driven by experimentation, which leads to more models in production. To support this endeavor, we needed to concurrently up-level our infra maturity. And at the start, we were doing fine. The infra groups working alongside our machine learning engineers, or MLEs, knew which handful of models out there were important to monitor. But as we continued investing more in AI for better recommendations across Instagram, the number of engineers and models quickly outnumbered the teams that supported this foundation. We knew we needed to get ahead of this problem. But how did we get here? Why are we expecting so many models? Well, within Instagram, multiple things are ranked. Your Instagram feed, your reels, your stories are all personally ranked to you. But it goes deeper than that, including what comments you might find the most interesting, what notifications you might consider important, and what the next person you might want to tag on a post. Within each surface, we have a ranking funnel. We divide in layers for retrieval or sourcing, early stage ranking, and late stage ranking. We have multiple layers because within each stage, things get progressively more expensive. We would like to operate on fewer candidates, so that's why we opted for a funnel for this analogy. The source and rank pattern can be found throughout all of our surfaces. In terms of experimentation, within each surface and stage, we want to give our engineers the opportunity to experiment on each of these models to adjust and optimize ranking. For all these permutations, you might have one production model and 10 experiments. The net result is a large number of models serving user traffic. This is the journey to 1,000 models, scaling Instagram's algorithm without the reliability nightmare. So what were our risks? For discovery, we didn't know what was out there. Product ML teams were maintaining separate sources of truth for their models in production. It was impossible to build or scale automation out that ingests and operates on everything under Instagram's scope. We either monitored everything or nothing at all due to signal versus noise ratio we wanted to optimize for. For release, we didn't have a consistent way to launch new models safely. We can't maintain any information about models because our catalog would just quickly go out of date, preventing this catalog from becoming effective. And the process was also slow and impacting ML velocity. For model health, we lacked a consistent definition of prediction quality. Quality issues went unnoticed. Product ML teams were left to build their own monitoring and observability solutions, if any. And because of this, we lacked a unified standard upon which we could strive for and adhere to. To fix this, we built a model registry, the first of its kind at Meta. For release, we made innovation faster and safer at scale by building launch tooling. For health, we introduced a model stability metric and operationalized its use across IG models. This wasn't a new concept, but it was a new approach to unify its application for all of our ML use cases. These solutions were not independent, but relied on each other for a successful ecosystem maturity boost. Let's start with the foundation, the model registry. I'll pass it off to Luke to talk about this.
Thank you, Sing Sing. Managing a large number of models in production comes with many discoverability challenges. Often was the case of conversations like these, where infrastructure on calls faced inbound alerts and escalations for seemingly severe issues, and often was the case that these issues were in fact benign. Why was this a problem? First, ranking models were referred to by nothing more than an integer ID, and what these numbers meant was tribal knowledge spread across many different machine learning engineering teams. For example, how does an on-call interpret the statement, model 12345 has a 20% error rate? If an on-call is fielding such an alert, we must answer a few questions. Is this impacting the user experience? Is this an immediate urgency requiring my attention right now? Does this require a 2 a.m. alert? Conversations like these and questions like these were frequent, driving significant operational toil and a poor on-call experience. This would not scale with our pace of ML adoption, nor was this a healthy mode of operation for on-calls whose continued presence was critical to business operation. So we set out to solve these problems, starting with the development of the model registry. So what is the model registry? At its core, the model registry solves two problems for us. First, it maps models to their business function and criticality. Additionally, it provides a unified foundation upon which we can lever for additional automation. To deliver the model registry, we started with a broad introduction and enforcement of high-quality model types, which map models to the business function they support, along with their position in the ranking funnel. From here, we associated these model types with a criticality strongly tied to their business importance. We took these concepts and codified them into a structured configuration, which houses this metadata and serves as our foundational source of truth. Building the registry unlocked several key benefits for Instagram. Its use formed a trusted foundation upon which on-calls can rely upon for incident management and response. This also reduced the operational overhead associated with many aspects of model management, some of which we'll detail in just a bit. Finally, the model registry unlocked the potential for automation to scale our ecosystem to a pace on par with our rapid ML innovation. Let's talk more about what we've done with this new power. To kick off this next discussion, I'll pass back to Sing Sing to talk through key developments in our model launch ecosystem, which help us keep moving fast.
Thanks, Luke. We talked a bit earlier about how some of the 1,000 models are experiments. But what does that mean? How do we convert an experiment into a new experience for billions of users? Well, to improve IG's ranking, our engineers start with an environment where we can isolate our changes. They create a new model, and this engineer can create a new model for every change they want to make and send a fraction of traffic to it. After that experiment is reviewed and approved for launch, we change the experience for the majority of users by redirecting users to the new model, and it becomes our new baseline. Simple, right? Well, in the best case, iteration was very slow and DevX was painful. Let's walk through an example of what life was like before tooling. Let's say it's Monday, and we want to start kicking off a load test by creating a clone of our candidate to overload. We want to do load tests because we want to know exactly how much throughput that a single replica of this model can handle. We'd spend all day debugging and trying to accurately measure how much load we can handle by adjusting live traffic. By Tuesday, we'll hopefully have enough data to work with and do some calculations. By Wednesday, the team would go to leadership for approval, and at the same time, the infra teams would be prepping the capacity that these models needed and checked for any configurations that match all of our expected customizations. There was also a difference between the settings we would configure for an experiment versus settings we would configure for a model we planned to serve billions of users. By Thursday, we would have finally started the launch process, slowly shifting traffic and resizing services in lockstep. If we didn't finish that Thursday, we'd pick back up the next day. And then when the launch was wrapped up, each MLA team would have to remember to update their alerting setups. In the worst case, the users would go for it without any prep work, thinking that our infra could magically keep up because the DevX through this official process was so slow. This caused sevs because we were trying to scale to millions of users at a time, and the services weren't pre-warmed. There was also a risk that we might not even have the resources in the total pool to support this new model if we didn't do this estimation. And the new service could have been made more expensive resource-wise. So we would have been scrambling. We did multiple things to fix this. The first of which was to start splitting our hardware into virtual pools and isolate them. This empowered leads to distribute capacity and supply according to product effectiveness. For example, this framework allowed us to reserve and bootstrap a new pool for Threads, the newest member of our family of apps. This framework also empowered teams to start making their usage even more transparent by enabling separation between the layers in their quota hierarchy. Together with partners in our AI infra teams, we also put together a more ideal flow end-to-end, and scaling our process and enabling Instagram to reliably iterate faster. Estimations went from this tedious ordeal that took days into a one-click process that finished within 1 hour using recorded traffic. No more messing around with live traffic. For approvals, we developed a policy that allowed teams to sign off on launches that didn't have additional costs. With quotas, there was less red tape around planning across different surfaces at the team level because these quotas simplified those discussions. If a team would stay within their quotas and had enough buffers within these pools, they had the green light to proceed. And this unlocked our ability to parallelize each launch. For prep, checklists turned into validations. Traffic shifting also became automated. which freed up an engineer who'd previously have to babysit the launch all day. And finally, by leveraging the model registry, automation was built to enable observability and alerting with no additional operational costs. Ultimately, we took a process that could take up to a week down to less than a day, and we could even run them in parallel. Within launch, we integrated with model registry so that our model type records would reflect the new truth. Marked in yellow here is the monitoring configurations we expected our new models to inherit. Not only did the registry help simplify our launch process, we unlocked a new power by harnessing the benefits of source control. Lineage. Coming back to what we all learned earlier, model registry served as a place to define and enable alerting, which obviated the need for teams to implement their own bespoke detection. And by building links to the model registry, we lifted the manual burden that could sully our trust in it by tying it directly into the model lifecycle itself. Altogether, we cut down on the class of SEVs related to launches as we added more validations into the tooling. We went from only being capable of hand-holding 1 or 2 launches a week to supporting more than 10. And while our intent was initially to help our MLE partners, we found that the time we spent working on this release process cut down as the lifecycle became more self-service. With a handle on safe transitions across models and unlocking iteration speed, it became increasingly important to unify our definition of model health and operationalize it for our scale. And so now I'll pass it to Luke, who will talk about model stability and wrap up our key takeaways and future challenges that we expect to face.
Thanks again, Sing Sing. Now let's talk a bit about why measuring ranking model health is unique. Models produce scores predicting user actions. For example, the probability that I like a photo if it's shown to me, the probability that I comment on that photo if it's shown to me, or the probability that I follow the account associated with uploading that media. Unlike traditional request and response idempotent backends, the quality of a model's response carries a significant importance to the end user experience. Let's frame this with a few examples, considering a user who is a huge fan of golf, but doesn't really enjoy cooking content. In this leftmost image, we have a traditional image of availability, or lack thereof, where the user doesn't get any response at all. We're well familiar with this concept. On the rightmost image, we have the ideal user experience, where the user gets content back and it's engaging and relevant to their interests. Our focus now is on upleveling maturity in the availability domain to focus on this center experience, where the user receives content, but the content is irrelevant to them and doesn't match their interests. When we are recommending this type of irrelevant content, the user experience clearly suffers. The model stability metric was designed to make it easy to measure this accuracy and detect inaccuracy at our large scale. Let's discuss a bit about how this concept works. In our funnel, ranking models are complex and produce multiple output predictions. In order for us to claim that a model is stable, we must first claim that each underlying prediction is stable too. In this example presented here, we have a multitask multi-label model, or MTML for short, predicting 3 user actions: like, comment, and follow. Let's move on to discuss how we define prediction stability for such a model's predictions. When measuring the effectiveness of a predictor in a ranking model, we commonly look at 2 evaluation metrics. The first being calibration, which answers the question, are we over or under predicting this user action? An ideal calibration floats around 1 in steady state. The second evaluation metric commonly used is normalized entropy, or NE for short. This metric answers the question, how well can we distinguish between action and inaction? Lower NE is typically a better indicator of this model's distinguishing power. With these evaluation metrics, we've been able to analyze historical trend to construct healthy thresholds for each of these indicators. When we encounter a breach of either of these thresholds, we know that a prediction is producing inaccurate results and can alert indicating this is the case. This forms the basis of a service level indicator representing the health of a model prediction. In the example presented here, you can actually see a clear breach in prediction stability right around February 17th. To restate, from these individual indicators, we can build two things. First, an SLI, or service level indicator, representing the real-time model health that we can alert on when thresholds are breached. This indicates there's some sort of problem with the underlying prediction. We do this by taking a logical AND of the underlying calibration and NE health to claim a prediction is healthy, forming this real-time binary health indicator you see presented in this example chart. Second, we can build an SLO from our SLIs, or service level objective, which catalogs the aggregate view of SLI attainment for predictions over a period of time. At our large scale, and with a large number of production models, this is the key that enables simple understanding of the entire product surface's health. We're now able to quickly answer, for example, that the stories surface is 99.9% stable over the past month. Without this unified definition of model stability, we were really unable to make this claim. So let's recap where we are with model stability. We have over 1,000 models in production. Each of those models produces many different predictions. By operationalizing the model stability metric, we've gained a common solution for measuring model health and model stability over time. And now, for the first time, we've unified our understanding of recommendation health for all product surfaces at Instagram. This has unlocked our ability to build generic alerting and repeatable investigative flows to guarantee detection and timely mitigation of prediction inaccuracy in prod. And with the model registry serving as a foundation for housing these definitions, we've been able to build automation to power its population. Zooming out a little bit, after a close call, with the development of the model registry, step function improvements in our launch ecosystem, and unified definition of ranking model health, we've grown closer to bringing parity between infra-maturity and the scale of models our users depend on for an engaging experience. So what have we learned from this journey? First, understanding the infrastructure is really an important foundation for building the right tools for the job. Without a strong handle on what we're working with, what's important, and what the business purpose of our models are, our job becomes increasingly difficult. Second, helping our colleagues move fast means that we all move faster, ensuring the pace of innovation does not slow down while also unlocking internal productivity dividends on the infrastructure side. Finally, reliability of our ecosystem, especially considering the recommendation system domain, must evolve beyond the basics of available and also consider the quality of results we give to our end users. There are, of course, also ways we can continue improving and new challenges on the horizon. Looking ahead to the future, one of our next challenges involves building solutions to ensure that our pace of innovation continues with an increasingly diverse set of hardware in production, which presents new challenges pertaining to heterogeneous hardware management as our fleet continues to grow much larger. We look forward to diving headfirst into these problems as we continue on this journey, scaling our recommendation system to new heights.